Hi guys, Miss Malmos here. I wanted to teach you guys this lesson myself and make it as personal as possible. So I included this video of me with this filter to just make it a little bit more fun and a little bit more like me and the way I would teach it to you if I was really there. So what I'm hoping from you guys, what you'll be able to do by the end of this video is explain why objects fall at equal rates. So I'm going to highlight that because that's really the big idea. We know that in a vacuum, a bowling ball and a feather will fall at exactly the same rate. The question that we haven't really talked about is why is that? Why does a bowling ball fall at the same exact speed, at the same exact acceleration as a feather when there's no air resistance? You would think that something with like a large mass, like this big boulder, would fall maybe a little bit quicker than something with a small mass. And the reason why I think we tend to think that is because a large mass tends to mean that something has a large force on it or a large weight. Whereas something with a small mass tends to have a small force acting on it or a small weight. And in our minds, it makes sense to think, okay, if I push my shopping cart with more force, the shopping cart's gonna go faster, right? But that's really not what we're comparing. We're talking about pushing an empty shopping cart with less force, and it's probably gonna move pretty easily, right? Because it has less mass. And then pushing a shopping cart that's filled with stuff with more force. And it's probably going to move at about the same speed as the empty shopping cart. However, it took a lot more force for us to get that shopping cart to move. So when we're changing two variables here, mass and force, we really got to talk about not just one of those variables, but both of them. So when we're going through today's lesson, I'm going to talk about not just the weight of objects or the mass of objects. I'm going to talk about the weight to mass ratio. And ratio might mean a new word for you. I'm going to underline it and kind of define it over here. A ratio is a comparison of two numbers. What I need to be able to do is compare the weight to the mass in a ratio. That weight to mass ratio is what's actually going to determine how quickly objects accelerate. Now, hopefully, we should be able to kind of describe these ratios as a way to explain why falling objects fall at the same rate. So that being said, I'm going to be using a couple of color coding devices and calculators. So if you've got those things, great. If you don't, you might want to pause and grab them. But I'm going to move on to the next slide. So that being said, we're going to do a throwback here all the way to chapter 3. Our guy Galileo, he was the father of inertia. We made that inertia timeline, and one of the pages was dedicated to him. He actually contributed quite a lot to physics. Inertia was his biggest contribution, but he also was the guy who did the experiment on the Leaning Tower of Pisa, where he dropped a cannonball and a pebble, and he saw that they fell at these same exact rates. Or in other words, they accelerated equally, regardless of their mass. Now, this is true for any scenario where air resistance is negligible. I'm not spelling negligible right. Hold on, let me try again. Negligible. There we go, negligible. If air resistance is present and it's noticeable, then this is going to be approximately true. What I mean by that is that if we were to drop a ping pong ball, if you've ever worked with a ping pong ball, they're very light, they're very hollow. We would see that they fall, but air resistance slows them down as they fall. Whereas if I were to drop a golf ball is very heavy and very solid. It'll fall straight through the air with very little effect from air resistance. So a golf ball is going to fall at the same rate as a bowling ball because, again, air resistance is negligible. But for a ping pong ball, air resistance is going to have an effect. So we're not really going to focus on situations that involve air resistance. In fact, we're just going to focus on situations that are truly called free fall. What I mean by free fall is that something is falling and experiencing only one force. So this pebble, for example, if it were in free fall, it would only feel one force, the weight of its gravity. If there was air resistance that was acting noticeably and pushing it upwards, we would no longer consider the pebble to be in free fall. So as long as there's only weight, then that object's going to fall at the same rate as any other object in free fall. So let's talk about why a pebble might fall at the same rate as a bowling ball. If we move on to the next slide, we've got Galileo's experiment. I'm going to label this picture as Galileo's experiment. He got on top of this leaning tower of Pisa, and he did. He got a heavy object, a cannonball, to be precise. I'm going to highlight that actually. He got a 10-kilogram cannonball and a 1-kilogram stone. So very different masses for sure. One was very heavy, one was very light. And he dropped them at the same time from the top of the tower. And what do you think he saw happened when they hit the ground? They hit the ground at the same time. And people were shocked. They expected the cannonball to hit significantly sooner than the stone. But no one had really ever done an experiment and tested it. Everybody just assumed a heavier object would hit the ground well before a lighter object. So when he did this experiment and they landed simultaneously, it really rocked the world. Why would this happen? Something heavy, you would think, would get more force, causing it to fall faster. So let's compare the force of the stone and the force on the cannonball. So I've got this comparison here, right? I'm going to compare these two variables, mass and weight, with two different colors. The mass of the stone is 1 kilogram, whereas the mass of the cannonball is 10 times more, 10 kilograms. So what does this mean? What am I talking about when I'm comparing mass? What I'm talking about when I'm comparing mass is the inertia. Something with less mass is going to be easy to move. Think about an empty shopping cart. An empty shopping cart has very little mass, so it's very easy to push it around the store. Whereas a full shopping cart or something with a lot of mass, like the cannonball, is going to be very hard to move. Why? Because it has a lot of inertia. So it resists moving and wants to just stay put. So we've got already this difference in inertia. So just looking at the mass, something that's easy to move, I would think, would fall very quickly because it's easy to fall. And something that's very heavy, it has a lot of mass, I would assume would resist falling a little bit more. So we've got this easy movement for the stone and this very difficult movement for the cannonball. But let's talk about forces now, because we know that forces are definitely at work here. For the stone, the force of gravity is only 10 newtons. And if you're wondering where I got that value from, remember on Earth, the strength of gravity is 10 newtons per kilogram. So this means for every kilogram of mass, Earth is going to exert 10 newtons of force. So this 1 kilogram stone is only going to feel 10 newtons of weight. So what that means is there's not very much force, or there's a small amount of force. So think about when you're pushing a shopping cart. If you have an empty shopping cart, do you have to push it very difficult or very hard? No, you push it very easily, very lightly, very little force. Now let's say you filled that shopping cart to the brim. Not only is it going to have more mass, there's going to be more weight to it. 10 kilograms worth of mass is going to be 100 newtons worth of weight. So what that means is that the Earth is pulling with a large amount of force, or a lot of force. So it's pulling very, very difficultly, or very strongly. That's the word I'm looking for. So there's a strong pull happening on the cannonball, whereas there's a very light pull happening on the stone. So how does this translate to acceleration? Well, if I wanted to figure out the acceleration of the stone in the cannonball, I would need to use Newton's second law. So I'm going to remind you guys of Newton's second law equation right here. Newton's second law says that an object's acceleration equals the net force divided by the mass. Now, in order to know the net force, I kind of need to know what the diagram looks like for all the forces acting on it. So I'm going to do a quick sketch. My stone is in free fall. I'm going to make that note here, which means it's only experiencing one force, gravity. Now, the force of gravity is very small. We know that it's only 10 newtons worth, so not a ton. So I'm going to plug in 10 newtons for my net force, and then my mass is 1 kilogram. Now, when I divide these, what I'm going to get for my acceleration is 10 meters per second squared. Crazy. That's exactly what we know acceleration of free fall to be. So this is where that value 10 comes from, taking that weight and dividing it by the mass. Now, do you think the same thing's going to happen for the cannonball? Maybe. If I were to plug into the same law, force divided by mass, I'm going to be using different values. First of all, the mass of the cannonball is significantly larger, 10 kilograms. However, the weight is also different, 100 newtons. So if I divide 100 by 10, that gets me 10 meters per second squared. The same thing I got for the stone. Kind of crazy that I got 10 for both of them. So even though the stone is experiencing less force, because it also has less mass, 10 divided by 1 gets me 10 meters per second squared. And even though the cannonball is experiencing a whole lot more force, it also has more mass. So when I divide those values, I still get 10 meters per second squared. So what does this mean? What this means is that for any falling object, when I divide the weight by the mass, I'm going to get the same exact ratio, or an equal ratio. I guess I should put same right there. That would make sense. So when I use that word ratio, what I'm talking about is this fraction we get from Newton's second law, taking the weight in newtons and dividing it by the mass in kilograms. For any object, if I were to take its weight in newtons and divide it by kilograms, what I should get for that ratio every time is 10. So mathematically, the ratio is what really proves all objects are going to fall at the same rate. But if we think about this in terms of physics, I like to think about it in terms of this push and this resistance. So when I think about the cannonball, I have a lot of force acting on the cannonball. When I also think about the cannonball's mass, it has a lot of mass, which means it has a lot of resistance. So even though I'm pulling with a great amount of force, that great amount of force isn't going to cause the cannonball to move very much. Why? Because its mass is resisting moving. So what about something that's small, like the pebble? The pebble is a very small mass, which means it has a small resistance. It's easy to move the pebble. So if it's easy to move the pebble, do I need to exert a lot of force to get it to move just like the cannonball? No. In fact, I need very little force to get the pebble to move. Why? Because that pebble doesn't need as much force to get going. It has a small mass, and therefore is very easy to get it to change its motion. So easy to move means I only need a little bit of force. Whereas for the cannonball, difficult to move means I need a lot of force. But the ratio of force to resistance is always going to be equal to 10 meters per second squared, which is what this lowercase g stands for. I apologize for the notifications. So that being said, how are we going to practice explaining this relationship between weight and mass? How are we really going to demonstrate that we know why a cannonball and a pebble fall at the same rate, or a bowling ball and a feather fall at the same rate in a vacuum? Well, I think the more creative we are, the more we tend to learn and then remember how to do some of the things that we're learning. So my goal for you guys is to accomplish this objective in the most creative way possible. What we've got on the next slide is a comic strip. I'm going to go through and read the comic strip for you guys, point out some interesting things. Feel free to read along with me, or you can pause and then play when you're ready to go. So we've got a situation here. We've got a neighbor. She's hanging outside her window, and she's got a big bag of clothespins that's very heavy and a single clothespin that's very light. So she asks her neighbors, if I drop the bag of clothespins and the single pin at the same time, which is going to fall to the ground first? So the boy in the red shirt says that's easy. The bag of clothespins is heavier, so that means gravity's going to pull on it with more force. So the bag of pins should accelerate more and hit the ground first. So I'm tracking what he's saying, right? More force means it's gonna go faster. But the kid with the purple shirt disagrees. Purple shirt kid says, not true. The bag of clothespins has more mass. So that means it's got more inertia. So it's gonna be less responsive to gravity, and it's gonna lag behind the single pin. So I get what he's saying. He's saying because the bag has more inertia, it's gonna resist falling, and it's not gonna fall as fast. So that makes sense. So he's saying the single pin should hit the ground first because it's going to be easier to move. So then when she drops it, plunk, plunk, they hit the ground at the same time. And if you notice, there's this eavesdropping neighbor to the right who gets involved. Sorry, gang, a tie score. And the boys are like, how come? What happened? She says, since the bag has both a greater weight and a greater inertia, one offsets the other. The accelerations end up being equal. So what she's describing here is that because there's also, just because there's more weight, doesn't mean that's the only thing affecting the fall for the bag of clothespins. Because it also has more inertia, it resists that greater weight, and it falls slower than what you would think a clothespin would fall at if it experienced the same force. Now, the reason the clothespin doesn't fall faster than the bag is because it has less weight acting on it. So it's not being pushed to fall very fast. Like the bag of clothespins is having to be pushed a lot just to get it to fall. So by comparing that ratio of the amount of force to the amount of mass, we end up getting equal rates of acceleration. So we can see that this comic strip really does a good job of explaining the why. It doesn't just explain that they fall at the same rate. What it's explaining is that there's a reason why they both fall at the same time. Not only that, it talks about confusing misconceptions. So it talks about why someone might think the clothespins would fall faster, or someone might think the single pin would fall faster. So it addresses misconceptions as well as really explaining why they fall at the same exact rate. So my goal for you guys is for you to make your own comic strip, one that gives you an opportunity to do this in a creative way. You're going to make a comic strip that's colorful, creative, and does two things. It explains why objects with different mass and different rates fall at the same rate. And I'm going to add to this, it also needs to address misconceptions, or why someone might think they don't fall at the same rate. You're going to want to write this down in your notes so you don't forget. So I've got a rubric for you guys that I'm going to use to grade your comic strip. Just like for your timeline of inertia project with the foldable, I'm going to give you guys an opportunity to earn extra credit by making this just over the top, creative, colorful, and really thorough in explaining that mass to weight ratio, as well as addressing why someone might be confused and think that they don't fall at the same rate. So really, the more you exceed the expectations on the rubric, the more opportunities you're going to get to earn extra credit. So you have your full arsenal of color coding tools in my classroom. There's plain white paper as well that's been laid out on that front checkout table for you guys to use. You're going to have a limited amount of time to work on the comic strip, so you're not going to necessarily get as much time as you need. Whatever is not finished, you're going to take home, complete the comic strip, and then you're going to turn it in next week when I come back to class. So that is the goal. After the comic strip has been started, there is an assignment that I have for you guys where I'm going to want you guys to practice doing this mass to weight calculation. So that assignment is called the Lesson 6.6 assignment. This is going to be homework if we do not finish it in class. So make sure that you get the comic strip started and that you complete that lesson 6.6 assignment for homework. So hopefully this lesson was clear. I'll make sure that when I come back, I'm available for questions, but I'm really hoping that personalizing it this way made it a little bit easier for you to understand. Have a great weekend. I miss you guys.